Hi, it's Carly McAvoy. I'm talking about Bernoulli trials today. Repeated trials of an experiment are called Bernoulli trials if we meet the following three conditions. One, each trial has only two possible outcomes. We typically call those success and failure, even though a success may not be a positive thing. If we were looking for a genetic mutation and we found it, that might be a success for what we were doing. Either they have it or they don't have it. But having it doesn't sound like a success, but for our trial, it would be a success. The probability of success P remains the same for each trial, so it doesn't like, oh, sometimes it's 40%, sometimes it's 50. No, it has to remain the same. And that the trials are independent, meaning the outcome of one trial does not influence the next one. So let's look at some examples really quick here. A basketball player makes about 82% of her free throws. Assuming the shots are independent, find the probability that in tonight's game she will do the following. She'll make her first free throw will be on her fourth attempt. In order to do this, we need to know the probability of success, which is 82%, and we need to know failure. And so in order to find the failure, we take 1 minus P to find Q. Q is our failure, right? So for this one, if we take 1 minus 0.082, because 82% was her success, we would get 0.018. So we know that our probability of success is 0.82, and of failure in this case, or our Q, is 0.18. What we want her to do for our particular thing is she's taking 4 attempts before she makes her first free throw. So that looks like Q, 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 because she misses, and then finally P, she makes it. And so Q is 0.018. We're multiplying these together because they're happening consecutively in our trial. So we have 0.018 3 times multiplied by 0.082 at the end when she finally makes it, which we can write in shorthand as 0.18 to the third power times 0.82. And if you multiply that, you get 0.0048. So typically you want to write your percentages to the hundredth of a percent unless you're asked differently. But so if we move that over 2 decimal places, 2 places over, we have 0.48% chance that she would miss her first free throws and make a fourth one, because she's got a pretty good percentage rate. So it would be unusual for her to miss 3 and then finally make the fourth one. What if you were asking, what if she made her first free throw on her 9th attempt? That means she would miss 8 times, and finally on her 9th time, she'd have a completion or actually put the ball in the basket. That should not happen very often because she's got 82% success. So if we look at this one, it's just like the other one. We have Q 8 times followed by P. And so instead of writing out 0.018 8 times, I would just say 0.018 to the 8th power times 0.082. And this is the number I got on my calculator. Now, if I was to move my decimal point 2 places over, you can see I'm still amidst the zeros. So we would say in this case, she has a close to a 0% chance that she will miss the first 8 and then make the 9th one. It just isn't probably going to happen for her because she's better than that. She doesn't miss 8 in a row like that. So it's a really zero, like we can just say 0% chance, even though it's not exactly 0, but it's getting pretty close to 0. Okay, and the third part of this in our last example, in part A, we looked at the probability that a basketball player would make her first basket on the fourth try, first free throw. What if we wanted to know the probability that she made exactly 1 basket in the first 4 attempts? We want to round that answer to the 100th of a percent. No, we don't care which of the 4, just that she makes that 1 out of 4. So we want to write down all the combinations of how she could make 1 basket out of 4. And here's what we can see. She makes the first one and then misses 3. She makes the second one, misses the first, third, and fourth. She misses the first 2, makes the third one, or she misses 3 and then makes the fourth one. Those are all the only ways we can say she makes 1 out of 4, right? So for each of these sets, we have 3 misses, or 0.018 3 times, and we have 1 where she makes it, which is 0.082. So the community property tells us the order doesn't matter. If you multiply in this order or that order or this order or that order, you're going to get the same answer because you're multiplying 4 things, the same 4 things. So there are 4 different ways to do that. So we would say if we want to know Up here, we just wanted to know what are the chances that she would make exactly one, but we know the last one is the one she would make. That's this probability right here. But if we want to know, well, what's the chance that she would make one, but not necessarily in that order, we would just say, well, there's 4 different ways to do that, right? These are all the 4 ways that she could make 1 out of 4 free throws. And so we would take that probability that we found before right here and multiply it times 4 because there's 4 ways. If there were 6 different ways, we would multiply by 6 because we're really, when we see the or, we're adding those together. This plus this plus this plus this. But we can just say times 4. And so then it looks like this. And so then we would say she has a 1.91% chance of making 1 out of 4 free throws. And that way we didn't specify that her 1 came last. We're just saying it's 1 out of 4. We don't care which order that it was in. All right, that's the video for today. I hope you have a fantastic day, and I'll see you next time.